So I am Ármin Zavada, and I will present the joint work written by Kristóf, Vince, and myself. So we like models, we like writing models, but why do we like writing models? It's because we want to use them and we want to extract information from these models. One of the ways we can extract information is to use high-level tools, for example, or techniques. For example, model checking is a technique to extract some assurances from behavioral models. So the idea is that the systems engineer or someone says or specifies some formal requirement or some requirement, and the model checker just gives an example or gives a proof that the requirement is always adhered to. The problem is that this requires formal knowledge, which usually is not part of the systems engineering curriculum. So this is a limitation that model checking has, and because of that, people cannot really use it as easily. So an idea that we could have is to simplify this and actually hide the information that we need, these formalisms in the middle, and hide all the ugly details that need to happen and we need to actually do in order to come up with the engineering. In order to come up with the formalization from the engineering models and the engineering requirements. So as we see that engineering languages and engineering models are knowledge bases, we can use them to extract data and to come up with decisions about our systems. Usually, engineering languages are traditionally operationalized. This means that there is an algorithm behind it that specifies exactly how it is executed. So programming languages and UML traditionally was operational. But there is a new trend of ontological behavior modeling where this is not the case. Ontological behavior modeling classifies behaviors executions in a 4D space-time, where 3 of those is spatial dimensions and 1 is a temporal dimension. And in such cases, it is not straightforward to model check and to run the same things that we could. So, for example, one example could be the Caramel and the SysML v2 languages, which is under development right now. So ontological behavior modeling has some unexpected challenges and the unexplored challenges that we need to finish and we need to explore and come up with solutions for. So a question could arise is that can we actually use our existing solutions to these problems or our existing tools that we have come up with during all these last decades that we have been doing formal verification. So to understand exactly the problems, we first have to understand some of the background behind these problems, some of the theoreticals. So traditionally on SysML v1, we had an operational language, which was token based. So for example, in this case, this is an activity diagram. There is a token that travels around in the model, and this is how the execution is specified. You always send out the token on all outgoing edges. If the token is at some place, then that place is considered to be executing, and we always wait for all incoming tokens. On the other hand, ontological behavior modeling doesn't really specify these steps. It specifies some constraints for us. So here, the step is a classification that it's classified as a step. And we have succession relationships between the specific steps. So for example, in this case, A must always come before C. But this doesn't give us a straightforward way to produce all the traces, valid or invalid traces that we might want to have. So operational semantics always gives us some algorithm that we can use, and we can construct the next steps from the current state of the system. And declarative or ontological systems or ontological semantics gives us a way to constrain the traces to the models that we use. It doesn't give us a straightforward way to construct them. It gives us a way to check whether a trace is conform to the given model or not. On the other hand, there are drawbacks to each of these semantics. So be it operational semantics, it's difficult to check the conformance of the execution trace to the original model, because we don't have a straightforward way to map back and check the conformance. And the declarative semantics, it is difficult to execute the model. Another question arises from this is, if we have two of these operational and ontological semantics, how can we check the equivalence between them? And this will be and I will come back to this at the third challenge. So from this challenge, we can come up with a research question, and that research question is, how can we actually operationalize such a semantic, such a language that has an ontology-based declarative semantics, because we want to operationalize, because otherwise we cannot really reuse our existing model checking algorithms that have been optimized to operational languages for the last few decades. So solution could be the following. So first we have the core language library. In ontological languages, we have some foundational axiomatic system, and the core language library builds on top of that foundation. In this case, it could be the caramel core layer. Our system model refines this core language library. It constrains the possible instance models that we can have. It refines the original library. And if we instantiate it in the 4D spacetime, it actually further refines the original system model. This is because our execution traces are not just steps, one by one steps. It is actually an instance model of the original system model. It actually is a refinement of that in a specific order. So the idea is to come up with a way to include operational semantics in the original knowledge base. So we could do that by extending the core language library with an operational library that is part of the ontology, part of the knowledge base that is originally in the language. And using this operational library, we can unfold along the ontology, unfold all of these semantic, all of these constraints along this ontology into the operational representation. And using this operational representation, we arrive at an analytic model, which is purely operational. And then we can reuse the same model checking techniques that we have developed during the last decades. If we then take the execution trace that this model checker gives us, it can be back annotated into the 4D instance model, and then we can use the same ontological techniques that we have we could do with the original ontological representation. So to reiterate, we can extend the ontology with operational semantics and then unfold it to the operational representation. This gives us some benefits. The first benefit is that the semantics is modeled in the language itself. It is no more hard-coded into the actual verification tool that we are using. It is modeled and can be refined as any model can be. And we also have explicit semantics. So it is readily apparent to the user and the language designer what the actual semantics of our language is in a given verification context. The second challenge comes from the fact that ontological representation has very intricate details. So, for example, here on the top, you don't really see the laser pointer. So on the top, you can see a simple two-state, one-transition state machine. It is transition from state 1 to state 2. The state 1 has some exit action, state 2 has some entry action. The transition is simple. It resets something on the toggle event. If we unfold the ontology as it would be unfolded in the original caramel SysML v2 ontology, we could arrive at the middle layer where all of the states are replaced by state actions, and all of the entry exits are also replaced, and we have some toggle resets and other actions that we can use. Unfortunately, the ontology goes a bit further, and the expressions and the assignment action is further unfolded into separate actions along this ontology. The problem here is that we already have the state space exclusion problem, and this just magnifies it. The reason is that we already have to take into account all the different orderings, all the different parallelisms of the original model. But here we also have to reason about the actual assignment action, and the ontological reasoner or verification tool has to come up with the exact instance model that adds and executes the given actions that we have specified here. But actually, our model checker doesn't really need that information. Our model checker is smart enough to run the assignment action, to run the reset action, to run any action that we need, because it can interpret these assignments more efficiently than just instantiating the assignment action in an ontological way. So that is the second challenge, is that how do we optimize these operational libraries, and how do we remove these unnecessary details that our model checker could interpret in a more optimized, or more efficient manner. And also, how can we use these abstraction levels? So, for example, the model checker might not even need this level of detail. It might know that what a state machine is. It might, for the model checker, it might be enough to actually know that there is a state there, there is a state there, and there is a transition between them, and just track that the transition event has happened. And that's it. Because there are certain situations where that information could be enough for us. Why bother with the more intricate detail? So our proposed solution to that is to abuse that our operation library is part of the original ontology. Use that these languages usually have some domain-specific libraries. So, for example, in SysML v2 builds on top of the caramel core layer, and then create a new refining operational library that is conformant to the domain-specific library and refines our original core operational library. As such, our optimized analysis model will then can be model checked as well, just like the original, and then backtracked into the 4D instance model as previously. One note here, however, is that we need to ensure that the execution traces are congruent to each other, because otherwise the 4D instance model will not be compatible or conformant with the original core language library. Congruence here means that if we hide some of the actions or some of the kinds of steps that our model takes, the different execution traces can be considered equivalent. So, for example, the abstract or domain-specific library hides some of the intricate internal steps that we do not need for model checking. So, for example, we can define a core operational library for SysML v2 as steps and successions. We can come up with some operationalized way to execute these step succession based language. For example, the tokenization that I introduced at the beginning of this talk, and then we can further refine it first at the action model library, where we can come up with expressions and actions that simplify the way the model is interpreted and model checked. And then further, if we do not really care about the intricate details of actions, we only care about the state, then we can come up with more high-level abstraction for state machines that hide these intricate action and control flow logic. Our third and final challenge of this presentation is the semantic conformance. So if we have two different semantics, then that's trouble, because we can't really trust our tools. We can't really trust that what we see is actually what we should get. We could try to prove the equivalence of the two semantics, which could be too hard and requires more research to actually go in that direction. Or we could prove the inclusion, the congruent inclusion, which is the minimal that we must do. Because if we cannot prove that, then we really cannot do anything in this case. So in this case, the operational semantics must conform to the ontological one. So it must be included as in the original semantics. So this operational library cannot produce invalid traces. So that is the minimal requirement we must have. But we should also try to think about a way to actually prove the equivalence between the two and try to prove that our operational library cannot produce can produce all of the original valid traces. And to reiterate, we have to make sure that this works even in the presence of these abstractions, semantic abstractions, because they hide much of the execution traces that we would have had. So the third and final research question that we specify is how can we actually prove the conformance of the declarative and the operational semantics. So the way to do that is actually inspired by a recent paper from 2022 by Doer et al. It's about verifying executability of SysML behaviors using the Alloy model checker. And what we can do here is twofold. So for first, we must make sure that the back annotation works. So we can back annotate from the execution trace all the way back to the 4D spacetime instance, and then using maybe that work or some other work that can check the trace equivalence or the trace between the 4D instance and the core language library. We can check here that the trace is indeed adhering to all of the axiomatic requirements that the original ontological language had. And if it does, then we can make sure that it is one of the traces that is valid. Well, again, this doesn't prove that the trace is equivalent, but it proves that it cannot produce anything that is invalid in the original ontology, because if it produced something, then we will catch it at the trace checker. Okay. So for these solutions, we implemented proof of feasibility to prove that it is actually possible to implement and do the things that we have proposed in higher level languages. So for that, we implemented a new ontological operational language, which is called OXSTS. It doesn't really, it's not really interesting at this point. What is interesting is that we implemented it to make a point, to prove that it is possible to use this approach in ontological languages. So it is inspired by Caramel. It extends Caramel with some operational semantics, for example, with variables and explicit stubs. And we saw that, we have proposed elements of the approach and elements of the language to the Systema V2 semantics working group as well. So we implemented a tool called Semantifier that uses this language to unfold the high-level ontological operational model into a purely operational model, and then can then be processed further by model checkers and code generators. This uses the same ideas that I have presented in this talk. So we have validated the approach. We implemented the OpenMB space mission SysML v1 state machine in OXSTS. For that, we implemented a state machine and activity diagram library, and using that, we implemented it in OXSTS, specified 40 different semantic formal verification requirements, which all have passed, and then it validated at least the semantical equivalence between the original model and the OXSTS one. So in conclusion, we concretized some open challenges in the context of ontological behavior models, such as the operationalization and the detailed execution basis of ontological behavior modeling. For that, we propose an approach of addressing these challenges. We propose to use and extend the original ontological language with operational elements. And then using these operational elements, we can implement the operational semantics of that language, and then use that model to define and refine these semantics. To demonstrate the approach, we have implemented a prototype tool and modeled the SysML v1 model in that tool. As future work, we plan to actually implement the original high-level semantics of SysML v2 behaviors using this approach, and use it as a case study in the future. Thank you very much for your attention.